All right, we're back. We are on page 139. We're talking about complex numbers in trig form, and they relate complex numbers and trigonometry, and that's really great for us because we're learning a lot about trigonometry. So let's see if we can figure out how to multiply numbers that are in trig form. So I wouldn't use this if I just had to do something like 2 plus 3i and 4 minus I, right? If I had to multiply those, I would just straight up do it, right? So that would be, you're going to get 8, and then you have minus 2 and plus 12, so minus 10i, and then you have a minus 3i squared, which becomes plus 3. So this is going to be 11 minus 10i. Hopefully, I don't know, sometimes I get those wrong. So I wouldn't do what we're about to do on this because those look really nice when they're in rectangular form. What we want to do is work out how to do it when they're not really nice in rectangular form, or when they look amazing, basically like unit circle-y, when they're written in trig form or polar form. So the first thing I'm going to do is I'm going to take our two complex numbers. So this is our first one, and then our second one. I'm going to take our two complex numbers, which are kind of in cis form right now, but it's expanded out, and I'm going to rewrite them using Euler's formula. So I'm going to say that z1 is r1 e to the I theta 1. And then z2 is going to be r2 e to the I theta 2. And so, I mean, it's not hard to keep track, but I'm going to highlight them anyway, because I feel like that's what a good student might do. All right, so we've rewritten them, and now we're just going to multiply them. So when it's written using Euler's formula, you will find that a lot of the rules that we're going to come up with just like jump out. You don't really have to do much to find them. So here, if I do z1 times z2, z1 times z2, that's going to be r1 e to the I theta 1, and then r2 e to the I theta 2, which is, so what I can do is r1 times r2, r1, r2, and then I have e to the I theta 1 times e to the I theta 2, but properties of exponents say that that should be e to the I theta 1 plus I theta 2, but I can rewrite that as r1, r2, e to the, I'm going to take I out and have theta 1 plus theta 2, or we could rewrite this. So this, I mean, this is the result. This is what we're looking for. So if I'm going to multiply things in complex numbers in trig form, I multiply the moduli, right? The modulus is r, or the absolute value of the complex number. So I multiply the moduli and I add the angles. That's what it comes down to. But if I write it in cis form, it's going to be r1, r2, and then cis theta 1 plus theta 2, which is pretty crazy. I mean, if you kind of think it through, right? What that's saying is, if you have your first complex number, this is actually like an interesting thing to look at. And I mean, I maybe should have set this up and done it in GeoGebra, but you know what I didn't do? That. So if this is like, let's say this is Z1, right? So this would be R1, and then this would be theta 1. Okay, so that's terrible. And now when I multiply Z1 times Z2, what I do is I rotate Z1 by the angle of Z2, right? Because I'm just adding to the angle. So I will get, say, I don't know, let's say this is theta 2, right? So I've rotated. And then if I was R1 away from the origin to begin with, I'm R1 times R2 away. So I scale it. So I multiply, I rotate, and I end up moving it away from the origin. So this will now be R1, R2, and this would be Z1 times Z2. So that's one way to think of it. Multiplying complex numbers is really like a rotation and what is it, like a dilation, I guess. So we're stretching how far it is from the origin, and we're rotating it about the origin. It's a very cool like geometric thing, I think. And so what are we doing here? All right, let's try to do one of these, and then maybe I'll come back in the next video and do the rest of them. So first up, I'm going to multiply these. I'm going to rewrite them in cis form or, well, we'll see. Let's call this Z1. Let's call this Z2. So Z1, I'm going to say, I see if I divide it by 4, I would get a unit circle point. So I'm going to say this is 4. And then I'll have root 3 over 2 plus 1/2 I. So that's going to be 4. I'll use cis form, cis. And then what unit circle angle is root 3 over 2, 1/2. That's pi over 6. So we got this. And then Z2. If I take out 5, I'm going to get negative root 3 over 2 plus 1/2 I. So that's 5 cis. Negative root 3 over 2, 1/2 is 5 pi over 6. So this is kind of interesting, I think. So Z1 times Z2 is going to be 4 times 5. So should I write that? All right, 4 times 5, and then cis pi over 6 plus 5 pi over 6. So this is 20 cis pi. Okay, so pi is a unit circle angle. So I'm going to rewrite this back in rectangular form. If I'd gotten like, I don't know, 7 pi over 17 or something, like that's not a unit circle angle. I have no idea what that is. I would just leave it in cis form. But because pi is a unit circle angle, I'm going to rewrite this. And I think the easiest thing to do is actually just like imagine where this is going to be, right? So the angle is pi. So I know that I'm like somewhere over, I'm somewhere over here. And then I know that it's supposed to be 20 away from the origin. So here, so this should just give me negative 20. So that's like an intuitive way of working it out. You could also just do 20, and then it's cosine of pi plus I sine of pi. So it's weird because they're pretty ugly. So the cosine of pi is -1 and the sine of pi is 0. So this gives me negative 20. Either way I do it. These are pretty ugly, complex numbers, I would say. I think. I don't know. Who am I to judge? But I think that these are not great looking. But when you multiply them, not only do you get something nice, you just get a real number, right? You get negative 20 plus 0i, I guess, if you want it to look like a complex number. So sometimes you get surprising results from these sorts of things. So I'm going to stop this here. I'll come back in the next video and do the rest of the page. And I will see you there.